we will look at a very simple finite state machine for flashing some lights. We've got 3 lights, a red light, a green light, and a blue light, and we want them to illuminate in sequence. So first the red light goes on, then the green light goes on, then the blue light goes on, and then the cycle repeats. The trick is that we probably do not want to flash these lights at the clock rate, because on the DE1 SoC board we have a 50 megahertz clock, and that will be way too fast. So we need to slow the clock down. For argument's sake, because I want to show you the unfactored finite state machine first and then the factored one, I'm going to assume that the clock cycle is 3 Hertz, so a clock frequency of 3 Hertz, and I want each light to be on for 1 second each. Let's have my starting state up here, being that the red light is on, the green light is off, the blue light is off. And I have to give my starting state a name. Well, I'll call it R because the red light's on, and I'm going to call it R1 because I need to keep the red light on for 3 clock cycles. That will, because 3 clock cycles corresponds to 1 second. So when I'm in R1, no matter what, I'm going to transition on the next rising edge to state R2, where again my red light is on and all the others are off, and by a similar argument, at the next rising edge of the clock I'm going to transition to state R3, where the red light's on and the next 2 are off. Once my red light's been on for 3 cycles, I then go to the green 1 state where my green light is on, and similarly green 2, 0, 1, 0, and green 3, 0, 1, 0. Finally, you should be able to guess that I go to B1 with 0, 0, 1, B2 with 0, 0, 1, and B3 with 0, 0, 1. And then after this, I simply go all the way back here again. Now, this is an example of, if you like, an autonomous finite state machine. There is actually no input. It simply transitions at the rising edge of the clock. And we've seen something like this before. Our counters behaved like this. Unless it was an up-down counter, our counter just counted. There was no other input to tell it whether or not to count. Anyway, this is one design and it's unfactored, but we see that the way it's drawn, it looks somewhat symmetrical. It looks like we could factorize it into one finite state machine does the counting 1, 2, 3, 1, 2, 3, 1, 2, 3, while the other one kept track of red, green and blue. And indeed even the states are labelled that way. The state's written as a letter followed by a number. The state factorizes. I could store the letter separately from the number. So let's have a look at how we can factor this finite state machine. Just before we do, this is probably the one time when you don't have to label the starting state, except it's a good habit to always label the starting state. I guess it doesn't really matter where in this cycle we started when we first switch on our device. In our factored design, we will have one finite state machine counting 1, 2 and 3, which corresponds to 1, 2, 3, 1, 2, 3, 1, 2, 3. And we'll have our second finite state machine going from R to G to B, corresponding to R, G, B, R, G, B, R, G, B. So we've got 2 finite state machines, and we'll have one of them controlling the other. So the one doing the counting, 1, 2, 3, it can tell this finite state machine when to move from red to green, and when to move from green to blue, and when to move from blue back to red. Okay, let's clear the page and actually implement this. Our first finite state machine is just a counter. So state 1, we'll worry about the output in a second. State 2, worry about the output in a second. State 3, worry about the output in a second, and repeat forever. Our second finite state machine is going to do our red, then our green, and then our blue. Going back to the top again. However, although these transitions occur at every rising edge of the clock, these transitions only occur after every 3 rising edges of the clock. So this finite state machine has to tell this finite state machine when to transition. So with that in mind, that means that, and it doesn't matter where we do it, we may as well do it at 3. We'll have 0, 0, 1, and the output from this finite state machine is going to let the red finite state machine know when to transition. The output of the blue finite state machine will be fed to the input of the red finite state machine. So let's call the output over here X, and then our transitions over here can be labelled by whether X equals to 0 or X equals to 1. So in particular, if I'm in the red state and the output of the blue machine is a 0, well, I want to stay in the red state. And the same for green and the same for blue. On the other hand, if the output is a 1, that's when I transition. And the only other thing is to put in the outputs to the LEDs, which is just from before, the red LED's on, the green LED's on, and the blue LED's on. And we now have our factored finite state machine. Just to be 100% clear, we know how this works. Let's play the game. Here's my marker, Mr. Cow over here, or is it Mrs. Cow, sorry. And here's my duck over here. And then at the rising edge of the clock, what happens? Well, over here at the rising edge of the clock, I go straight down here. At the rising edge of the clock, when we were back here, by the way, the outputs are 0. So that means that the input to the red finite state machines are 0. So at the rising edge of the clock, the cow goes down here and the little ducky goes round and stays here because the input was a 0. Okay, at this point here, the output from the blue finite state machines is 0, so that primes this one. At the next rising edge of the clock, we're going to go around 0 again. And this one, it moves at every rising edge of the clock. So there's a rising edge of the clock, cow goes down, chicken goes around. Now the output of the blue finite state machine is a 1. So next time at the rising edge of the clock, the cow goes around, but because the output was a 1 here, that means the duck goes down here. Same thing, next rising edge of the clock, bang, bang, next rising edge, bang, bang, next rising edge, bang, bang. Let's do it one more time, shall we? Next rising edge, bang, bang, next rising edge, bang, bang, next rising edge, there, here, and we're back to the start again. That's our factored finite state machine. We've got a blue one and a red one. The blue one is helping control the red one.